All right, welcome everyone at today's ASTRODEBATA. So our guest today is Pradosh Barun. He's a PhD student at Macquarie in Sydney. And before that, he studied physics and astrophysics in India, in Punjab, although he's from south of India originally. And he's working very actively on machine learning techniques for stellar spectroscopy. And he's visiting Europe now for how long you've been here? Like a month?
Yeah.
And you're staying for a few months more, so we're happy that he also visited us here for a week. And so please, Pradosh, you can start giving your talk.
Hi everyone, thank you Yanis for introducing. It's really a wonderful opportunity for me to kind of share my research with everyone here. I'd like to also acknowledge the continuous help that I've received from various members from the GALAH collaboration who have helped me immensely in completing this project. I won't say it's completed, but we are still working more on the research. So one of the main questions that we are kind of trying to tackle in this is regarding a very important problem that the current astronomy or the upcoming astronomy field is facing, that is huge amount of data sets that we have from different surveys, especially in the regime of low and mid resolution spectra. So it's very difficult to kind of get very efficiently the stellar information from the stars from them at a very quicker rate, which is where we think data driven methods like the cannon, which I'm going to explain today, would play a very important role. So what basically it does is, if you have a high quality or high resolution information for a few number of stars which are observed with low resolution spectra, I can essentially develop a model using the cannon which will then predict or learn the model and then predict abundances for a larger set of low resolution quality data. So you know the information for few number of low resolution data, and then you predict it for a larger set of data set using the cannon. That's the gist idea that we have under the cannon. Especially in my topic, I'm going to explain how we can transfer stellar information from a higher resolution survey like the GALAH data release 4, which was published recently, to a lower resolution, relatively lower resolution catalog, that's the Gaia RVS. So before going to the topic, I'd like to give a brief idea about the survey data that we are kind of using. So first, obviously, is the Gaia RVS. It's a mid-resolution survey catalog, which has about 11,500 resolution, and it has a very small spectral window. That's from 846 to 870 nanometers, and has the characteristic calcium triplet lines, which is very essential for measuring the radial velocities of the stars. It has nearly 1 million RVS spectra, which is available publicly, and after doing multiple selection criteria cuts on that, we are using 800,000 spectra for our analysis. I just want to make a note here that these 800,000 spectra are our test sample whose stellar abundances and various stellar parameters are going to be predicted by the cannon, which I'll show you later. For the training set, what we are doing is we are taking the stellar information, which includes temperature, surface gravity, and various other elemental abundances from the recent release of GALAH, that's the GALAH DR4. It's a relatively higher resolution survey as compared to RVS, and it has nearly 830,000 stars with 31 elemental abundances for those stars. Just to make a note that here on I'll be using the term stellar labels to kind of denote collectively to stellar parameters and elemental abundances, so that it's easy for me to kind of convey the message throughout the slide, throughout all the presentation. On doing a cross match between these two surveys, we find nearly 200,000 stars, which are common. And our training set is basically going to be a subset of these 200,000 stars, which is common between the two surveys. So how normally this complete algorithm sort of works? So as I explained, we take the subset of the Gaia RVS catalog and the GALAH DR4 catalog, and we have nearly 200,000 stars. And for the training sample that we select as a subset of these stars, we take the spectra from the Gaia RVS and the corresponding high fidelity abundances and parameters from GALAH as input parameters. Then we apply the cannon on top of these RVS spectra using those labels, the GALAH labels, as the model inputs. Then we train the model. Then once the model is trained effectively, we optimize all the parameters. Then we eventually use it to predict the stellar labels for the larger data set of 800,000 stars. And one of the key features in data-driven algorithm is you have to be very careful about that the abundances that you predict has to be within the error estimates of your training sample. So you can be as good as your training sample. You can't be better than that. Which means you have to find out a way such that we flag all those stars whose abundances or whose stellar parameters are outside of your training samples label space. This is why we use something called a 12-fold cross validation. I'll explain about it in detail later. Now, what exactly happens behind in the algorithm, the canon? So what it does is, as I mentioned earlier, for the RVS region that we have for this 846 to 870 nanometers, the canon actually models every single, associates every single flux, it associates every single wavelength pixel with the flux and the flux error at that point with the stellar labels that the GALAH provides. So for example, what you can see here is the capital F is the flux, N is the nth spectra, like the stellar spectra that we are considering, lambda is the particular pixel. So the flux at each pixel is actually a function of a vectorizing function, where L is the stellar label that we are taking from GALAH, and theta lambda basically is the model coefficient at that one wavelength pixel. Now these model coefficients are very interesting. What this basically says is which stellar parameter or which stellar abundance is prevalent at which pixel. So for example, we know that the RVS region has very prominent calcium triplet lines, which means the model coefficients at those particular pixels where the calcium triplet line shows very deep strength would actually give you a prominent value for those theta, for those model coefficients there. That's what it kind of encompasses the information into the model. And then once we have the total function developed, then we kind of optimize those model parameters, and eventually we get a likelihood function that would predict the corresponding abundances for the larger sample. So in my talk, I'm going to explain mostly two different models which I have worked over the last few months. The model one, of course, is the first one where a training sample includes nearly 14,500 stars, which is common to both the Gaia RVS and the GALAH catalog. And for those stars, we take obviously the spectra from the RVS and 8 stellar labels from the GALAH. That includes temperature, log G, and various abundances. And then we train the canon on this RVS spectra with these abundances, and eventually once the model is predicted, we then map it to the larger test sample of 800,000 RVS spectra. The model 2 is nothing but just a subset of the model 1, but with few additional criteria. What we are doing here is we are selecting only all the giants, so mostly with surface gravity less than 3.5, and we have increased the model space from 8 stellar parameters to 11, because now it includes zirconium, cerium, and neodymium, so basically neutron capture elemental abundances. This was essentially done just to see what's the capability of the canon in picking up these abundances even from the mid-resolution RVS spectra, and then eventually we do it on the 350,000 stars later on for the test sample. I'll be explaining mostly now model 1, and later I'll come up with what exactly we did with model 2. The best way to know whether your model actually predicted the labels is to see whether you are able to kind of pick up all the spectral features or sort of characteristic features that you know that it is evident from the RVS data or the Milky Way data. So here what you see is a keel diagram of the training sample, the 14,500 stars, but with the surface gravity, temperature, and the metallicity taken from GALAH. You can see the pretty much very beautiful structure forming, like you have the giants, you have the dwarfs, and the next plot that I'm going to show is the same exact 14,500 stars, but with the labels predicted using canon. So here you have the temperature, log G, and metallicity that were predicted for the same 14,500 stars with canon. You can see pretty much that the structures, the basic structure of the labels that were predicted remains same, which shows how robust the canon is in predicting these labels for the stars. Another way to check how well the canon predicted was to look for the one-on-one correspondence. So here in each of the plots, you can see on the x-axis you have the canon labels that were predicted with the model, and on the y-axis you have the GALAH labels for all the stars in the training sample. You can pretty much see that they stay one-on-one correspondent with very low error statistics, again which shows that the canon was able to get all the values quite accurately as compared to the training sample. Another way to put these plot would be to see for residual values. So here on the x-axis you have, in each of these plots you have the temperature from the GALAH on the x-axis, and on the y-axis is the residual values, which is basically the difference between the values that the Canon predicted as compared to the values that were predicted by GALAH. And in all of the plots you can see the very two prominent blobs, which is the giants and the dwarfs. So the giants are at the lower temperature and the dwarfs are at the higher temperature. You can pretty much see the distinction forming in all of the plots. Once we were very much confident that the training sample was good enough to see all the spectral features, the next thing that we wanted to do was obviously map it to the larger 800,000 stars, where we want to predict all the stellar parameters and abundances. But as I had mentioned earlier, we need to also be very careful about flagging all those stars which are not within the label space. That's why we use something called 12-fold cross validation. So what we do is we kind of distribute the training sample into 12 different groups, and then we train on 11 of those groups and find out the stellar labels for the 12th group. We do it for each of the group in the 12 divided sample. And then once we find out the standard deviation as a function of, let's say, root mean square value or sort of like a bias value which is inherent to the training sample, we map it to find out something called a label distance. So the label distance basically says that how far is your predicted label for a star from your training sample on which the model is trained. So if your star is outside of the 2 sigma label space of your training sample, eventually you're not going to consider that for your analysis. And what we found out was that out of the 800,000 stars which we were aiming to predict the labels, nearly 610,000 stars were within 2 sigma label space, which was a good retention, showing that the training sample that we used was actually pretty good in getting almost nearly 80% of the stars into our sample size. Here what you're seeing is the flagged 600,000 stars that we found after the 12-fold flagging condition. On the top you see the Kiel diagram with all the labels that were predicted, the surface gravity, temperature and metallicity that were predicted with the Canon, with the color bars plotting the metallicity distribution, and on the bottom it's exactly the same sample but more on a density map. You can pretty much see the red clump stars are forming quite accurately on there, which is a characteristic feature known, and kind of we were able to see that that's also something the Canon was able to pick up in the density map.
Pradosh?
Yes.
Why is the metallicity distribution so weird? It's very unnatural that you just have metal poor stars at the top. And
yes.
Metal rich stars only at the bottom.
Yeah. The thing is, like, the color map is not exactly showing the features here. There are actually features up here. But the color is like so fade. I have made it so fade so that you can see the total map. But if you actually isolate the different groups, you'll see the metal poor and metal rich stars present. And then we also try to compare our results with another group who were using convolutional neural networks to get the stellar abundances for the same sample of 800,000 RVS stars. I actually visited them last week. We had a very good discussion on these data set. So this is on the x-axis we have the Canon predictions, and on the y-axis are the predictions that were taken with the convolutional neural network modeling, and you can pretty much see that there is a consistency in the results that we are getting, except one, you can here see that the temperature range is kind of reaching a maximum point with terms of the CNN modeling. However, it goes up quite properly up to 7,000 Kelvin in the Canon model. So these are some of the features that we kind of were trying to compare it with the different results that the other groups have done. We also try to see how our results map with various clusters. So we took an overlapping sample of our targets with globular clusters as well as open clusters, just to see how the metallicities match up with our predicted metallicities. So here you can see the 4 globular clusters and 6 open clusters that we are matched with. The blue points are the literature values that we have taken, and the red points with the error bars are the Canon predictions. You can see pretty much that all the blue points are within the error statistics of the metallicities that we are getting for various clusters. Another thing that we wanted to see was to see if Canon would be able to recover the bimodal distribution in titanium. So this is one of the first studies where we are actually using titanium as an alpha proxy just to show in the RVS data the bimodal distribution. So here on the top left you see the Cannon, you see the Kiel diagram with a temperature log G from the Cannon, and the boxes that are marked up there, that's basically the same boxes that has been zoomed out here, like sort of zoomed here, but with the density maps provided. Now I want to bring your attention specifically on this particular box, where you see that the two different groups are actually forming up quite accurately. And when I actually map it into a larger scale and use Gaussian mixture modeling to sort of see the mean metallicity that's forming for the two different groups. So here you can see the cyan blue color and the yellow dotted colors kind of show the distribution of the thick and the thin disk that's forming within the sample. And the blue, the dark blue line, that's the sort of the knee metallicity, where you see the alpha abundance for the thick disk stars is reducing after that. Another way to visualize this one is to kind of see the distribution in different metallicity bin. So here as we go from left to right, the metallicity bin is increasing by 0.2 dex, and so as it goes like this as well up to 0.2. And the red line shows the high alpha mean metallicity that we found out from the GMM mixture modeling, and the black ones are the low mean metallicities for the low alpha stars. You can see that the gaps kind of increases and then reduces, which is kind of convenient, kind of similar to what the features are coming up there. And you can see that in this range from minus 0.8 to 0.4, where we normally see the knee metallicity, the two groups kind of show very accurately. And as we go towards the complete end, you can see the thin disk and the thick disk showing the majority of the population. And I'm not pretty sure if you can actually see this one clearly, the blue and the red lines. But I just wanted to give you a glimpse of how exactly the Cannon is predicting the spectra out of the abundances that it predicts for the model. So here the blue lines are the observed RVS spectra, the real observed mean spectra that we have for these two example stars, and the red ones are the predicted spectra that the Cannon has for those two stars. I'm not sure if you can see those lines clearly, but another way to kind of see how well it matches would be the residual plots. So the green lines that you see below each of these spectra is the residual plots, and you can see the residuals are basically the difference between the spectral fluxes at every pixel between the observed and the Cannon predicted spectra, and you can see that it's pretty much very small, which kind of is consistent with what Cannon is supposed to find the abundances for. And this is our paper that we published recently, and if you want to have a look at all the techniques, all the validations and all the results that we did, it's all there in that the QR code. I've also attached the QR code for the catalog that we published for the 800,000 RVS stars, where we have all the stellar parameters and abundances that we predicted for it. Now with this one was basically everything that we had for the model 1. The model 2, as I said earlier, is something that I'm currently working on, and this is sort of a subset of the model 1, but with surface gravity less than 3.5, so mostly RVS giants. And as I said earlier, it's exactly the same stellar parameter space that we use for model 1, but now we have included 3 neutron capture abundances, because we just want to see how efficiently the Cannon would be able to pick up the very faint neutron capture abundances line in this RVS region, and then eventually we do it, we train the model on top of it similar to model 1, and then we predict the abundances and parameters for the 350,000 RVS giants in our test sample. And similar to model 1, here is again the one-on-one correspondence between the different labels that we had. I want to bring your attention specifically to the bottom row, where it shows the one-on-one correspondence for zirconium, cerium and neodymium. You can see that there are some error statistics definitely in each of them, but moreover they kind of follow a one-on-one correspondence for the labels. We were also aware of this fact that since it's very difficult to find out individual spectral features for these neutron capture abundances in the RVS spectra, we needed additional statistical proofs to kind of show that the RVS has enough information for each of these individual species for the Cannon to pick up, which is why we used something, a technique which is normally used in exoplanet community called the cross correlation technique. I'll explain exactly what that one is. So essentially what you do is, let's say if you know a star whose Cannon predicted abundance are given to you, then you develop a template spectra out of those abundances, and you then shift that template spectra over the observed RVA spectra over a range of radial velocities. So what happens is every time you move over the observed spectra, you try to see how much your template spectra matches with that of the observed spectra for this relevant specific species over the total range of Doppler velocity. So what I mean is, here if you see, TI refers to the template spectra that we develop out of the models, out of the labels that we have for a particular spectra as a function of velocity, which is the radial Doppler velocity. And then we also normalize it. We normalize it essentially because we want to make the model such that at wavelength pixels where we have very strong features for, let's say, calcium or neodymium or anything, it will show up very clearly on the normalized spectra and then nullify all the other non-required elemental lines in our sample. And then once we get the normalized spectra, we calculate something called the cross correlation value. So here xi refers to the observed flux at a particular wavelength pixel, and then Ti hat refers to the normalized template. And this, when you vary it over a range of Doppler velocities, you try to see that how much of an information for a particular species is present in RVS. To explain this one in very simple words is essentially what you're trying to do is, we're trying to combine the strength of all the lines present for a particular species within a RVS region and then kind of maximize it such that it will be able, such that we verify whether they are sufficient or not. So let's say, for example, calcium has very strong three very strong lines in the RVS region. So then cross correlation would eventually pick up the information for these three specific lines of calcium over the RVS range and show very strong CCA values. Because as you move the template spectra, when it matches up clearly with the spectra very different from the noises, the corresponding CCA values will come very high. And since we are dealing with stellar spectra, so we don't need to worry anymore about the mean stellar frame velocity, because then it will be sort of a rest frame of zero velocity, which means here on the left, if you see at the stellar rest frame velocity of 0 km per second, we see a very beautiful peak that's coming for calcium. This essentially says that there is sufficient information within the RVS region for the Cannon to pick up. Because eventually what Cannon is doing, it is picking up the total contribution of all the lines for a particular species present within the wavelength. And that's essentially what we are confirming with using the CCA function. And you can see similarly for zirconium, cerium and neodymium, we are getting a similar very strong peaks, which shows that there is enough information in the mid-resolution RVS spectra which the Cannon is picking up. Now once we were very much confirmed that these are the information relevant present in the RVS region, one other thing that we wanted to try now was to wanted to address a scientific question, which was ultimately the main aim of my project. What we wanted to do was, we wanted to see that if we can use these abundances to kind of find new or maybe provide probabilistic approach to new accreted stars, for example, like the Gaia enceladus sausage, using only chemical information. So for that, what we did, we took an overlapping sample of our catalog of 300,000 RVS giants with kinematically selected GAC sample from Fulet et al. 2021. And for this sample, we used MCMC to develop a probabilistic model that will be modeled only on the abundances for these GAC stars. So essentially, it will kind of estimate how likely is a star a GAC star. How much is it similar to the Gaia enceladus sausage in the chemical space. It also has something called the model coefficients that we had similar in the Cannon, which basically says how influential is each element in determining GAC-like membership. For example, let's say if the calcium value shows up with a very high model coefficient value, it basically means that calcium is a very important factor in determining whether a star could be a GAC-like star or not. And then just to show you a glimpse of how the MCMC actually worked on, this is a corner plot where you see all the coefficients for the different elements that we used in an analysis on X and Y axis. And you can see that they're pretty much clustered around at a very good mean value, which shows that the cannon was able to reach at a stable point after various iterations. And we picked up these coefficients that were showing up the characteristic features of how the elemental space of the GAC-like stars work. And once we got those abundances, then we assigned probability to each of the star in the 350,000 RVS giants, whether they are GAC-like or not. And once we do that one, the aim was to kind of see whether we can use chemical information solely to distinguish the GAC-like stars, the probable GAC-like stars, from the other stellar populations like the in situ halo and disk stars. I want to note here that it is actually very difficult to do on if you just do chemical space distinction between the halo stars and the GAC-like and the GAC stars, because they are very much contaminated with each other. So which is why normally most of the research that is around this one uses both chemical and kinematic information. We wanted to see if there is a way to kind of not use kinematic information and just use chemical information just to find the distinction. One of the ways would be to not consider a 2D distribution but rather a 3D distribution of the chemical space. So here what you're seeing is all the pairwise combinations that we had for various elemental compositions. Here I'll just point out the colors so that it's easier for everyone to know. So in each of those boxes, the red stars represents the probable GAC stars that we think are probable GAC stars with a threshold of 55%. The blue colors are the Milky Way halo population, the green ones are the thick disk population, and the black ones are the GAC stars that we had cross-matched with Fuller et al. 2021. So ideally we would want those combinations where the red stars, that is the GAC candidate stars, would match similarly to the GAC stars that were cross-matched with Fuller et al. Because they are similar chemical space, and these sample space has to be different from the halo stars and the thick disk stars. That's the criteria that we wanted to put up for selecting various combinations. So what we did was we used random forest classifier to find out which is the best possible combination of various ratios that we can do, and eventually we found these three ratios to be pretty much good in separating these groups accurately. So here you can see in a combination of alpha and neutron captured abundances, you can see that the black and the red lines are coming up pretty much same in chemical space and kind of a little bit separate from the halo and the disk population, and this happens with all the three abundances that we had for the ratios. So this kind of gave us insight into understanding that these three possible ratios could actually be a way to distinguish the different groups. I just want to make note that this is not the explicitly, or I'd say unique combination of these abundances. There are actually some other combinations of abundance ratios that we have found out and which are showing these kind of features as well. I've just shown one of the examples here. I just want to give another broader picture where I'm comparing only with the halo stars, because disk stars are not a problem when you want to compare with the GAC population, because then you eventually can just rule out on the basis of metallicity. The problem comes up when you want to do with halo stars. And if you see those three combinations that I showed earlier, the red stars, which shows the probable GAC candidate, shows separate distribution away from the halo population. So this could possibly become one combination of abundance ratios that we can use to kind of isolate these different groups using chemical information only. But of course, I also wanted to check where these probable stars that we are predicting are on kinematic space, because I wanted to know whether it's actually satisfying all the kinematic known features for in the literature or not. So what we did was, for a subset of our sample, we wanted to see how it falls on the kinematic space. And you can see that that's the selection criteria that we put for the kinematic cuts for GAC stars according to Fuller et al. Who found out a purely kinematically selected GAC sample, and the same stars would fall at the ideal location where we want for the orbital action, and similarly for the phase space kinematic distribution where you see the stars forming up. Now again, these results that I'm showing are preliminary. We are still working on getting how easy, or how flexible are we in deciding the kinematic cuts for those stars. But yeah, this is something that I'm currently working on. I'm also working on something to understand how the particular combination of ratios that I included earlier would mean in stellar nucleosynthesis process. So I'll mostly leave with the summary slides for all the results that I've got. One of the things that I really am looking forward is to apply this method to the upcoming DR4 data, which is going to have 200 million stars. Because I think this is something, a data-driven approach is going to be a very important part, and it has to run in addition to the traditional spectral reduction techniques, which will eventually show you features quite efficiently in earlier stages. So thank you very much.
Questions, please.
Yeah.
I just wonder, this 800,000 RVS spectra, what is their typical signal to noise distribution?
I can actually show you that I had a slide on that. Yeah, this is something. Here what you see is the distribution catalog that we have for the total sample.
So of the order of 50 or something like that, okay?
Nearly 1/3 is less than 30 or 40 signal to noise.
Yeah, okay. Because I mean, the point is, okay, you had your Canon, your GALAH labels, let's call it this way. Then you trained Canon on that, and then your results are obviously very much impressive. I mean, because actually people tried this before. I mean, Canon was used before.
Yes.
True, you used the very last data release from GALAH as your reference. I mean, but now, I mean, one question is, why your results are so much better than everybody else's? Because I mean, for example, Casey and a number of other people were using this kind of same technique on same spectral data sets, true with a bit worse labels perhaps. But I mean, is this the whole difference, that now the data release 4 is so much better than everything else? Or what changed? I mean, because somehow people were struggling with very basic, let's say, problems here.
I mean, your doubts is actually really correct. There is a significant difference in the label prediction that I had when I dealt with DR3 and DR4. Because when I actually started my project, it was essentially, I was trying with the DR3 data. But I was actually seeing a lot of unexplained features when I was getting with the Canon data sets, which is why I shifted to DR4 data, and we actually saw a lot of improvement in the abundances.
Apparently this is all making the difference, right?
Yes, I mean, the labels do play a very important role. As powerful as your labels are, as good as your labels are, your training sample will be good. But I would like to also make a note here that the real important thing that actually comes around this process would be how you are training the spectra itself. Because the RVS spectra is eventually, you have a lot of, like nearly 1/3 of the spectra at a very low resolution spectral range, like from I'm saying from 15 to 30, there are nearly 300,000 stars out of this 800,000, which is why you need good labels to kind of match it with the different features. So if your spectra is already really bad, it becomes a very big problem. I mean,
and there are systematic problems as well.
Yeah.
Because I mean, for the second part of your talk, if I may, well, you know, calcium, no question about it. It's a saturated, nasty line, but I mean, it gives you fantastic radial velocity. Otherwise, it's a bit difficult to work with. Then, for sure, you have titanium, you have iron. But I mean, to have niobium and to have cerium in this signal to noise 20 or 30 or 40 spectra, so strong that you could predict. I mean, I wonder whether you have one problem. GALAH has 16,000 points in the whole spectrum and covers, well, not everything, but a good part of the optical range, right? Here you have just 1,000 points on 250 angstroms, and actually with, well, achievable but still relatively modest signal to noise, okay? And now you have your cerium and niobium and whatever determined by GALAH, and Canon learns what it is for these stars and then projects kind of what would you expect for the other stars, but which does not mean that a particular star in the RVS dataset has these labels. It just means that I mean, did you think, assuming that these are the same kind of stars as the GALAH training sample, this would come out?
Yes.
Which is an answer to the question, but not the answer to the abundance of this star, but of a typical star, this and there, on this and that diagram, that would on average behave this way, right?
Yeah.
Because otherwise I was a bit also surprised. I didn't understand completely your cross-correlation technique, but okay, you have some, I don't know where they are, but I suppose really faint lines of these exotic elements, okay?
Yes.
Hopefully, I don't know, I mean, I never heard about it, but there are more of these lines in the RVS.
Yes.
Okay, let it be. Of course, you have all the systematic problems of how accurate is your normalization and everything like that. But then, you are going with your spectrum across and varying the radial velocities, and actually, wouldn't you expect that these nice diagrams, which are symmetric and everything, would actually turn out nasty because you have very frequently the problem of superposition of different lines, and therefore, of course, if you change one element, it actually jumps to the wavelength of another element which is nearby, and therefore things are not centered around zero, but I mean somewhere. And this is not a problem of the element, but of the fact that you simply have your superposition of different lines.
Yep, I mean, answering to your first question, yes, you are absolutely correct that when you actually do the CCA function for a single star, the plots won't actually look very symmetric. It will have actually noises. What we have done is we have actually taken an average over 2,000 stars. So we have done 2,000 different stars.
If the niobium line is next to another stronger line of some other element, then your cross-correlation element would always try to push it to the stronger element, and you would have a systematic shift for all the 200 stars.
No, not
unless
necessarily.
you, of course, have different parameters. So
yes, actually, it's not the same for all the 2,000 stars. They have different parameters. We have actually chosen randomly 2,000 stars because we don't want to remain biased at strong calcium value. Or let's say I'm focusing also on neodymium, so I won't pick up a star only which has high neodymium, but rather 2,000 random stars which has various ranges of neodymium. Then what happens is the MCMs will understand which one is noise and which one is not, because then when you combine the strength from all the 2,000 stars, it will nullify the noise. Let's say the one which has very strong neodymium would not show the error bars very, it would not show high error bars. But one which has very low neodymium value, which means it's not a very good spectra, it will actually show higher error values. So if you combine the strength from all the 2,000 stars, the peak point would actually pop out of the error values. The error values will actually strengthen out. So the plot which you saw is actually the output after 2,000 stars were combined and shown the plots for different parameters.
I think that it would be really good to show where these lines are, how strong they are,
yes,
and so on.
yeah.
Because otherwise, you just suppose there is something there, and so far I never heard that these lines exist in the RVS range. I mean, so
the neodymium, cerium, and RVS has actually been observed with the original the RVS team actually used the Matisse algorithm to predict these three specific abundances only, which is why I picked up these three, because I wanted to compare our results and see how it was coming up. So these three are well studied in the RVS region already.
So how well would you be able to generalize this also to the prism spectra on Gaia?
Depends, like what kind of science you want to do. Like for example, actually the canon only depends on what kind of training sample you want to tend for, and that training sample has to be developed according to the science. So
would you be able to get metallicity and alpha out of?
Yes, depends. Yep, I have to check. But yeah, it's possible. It's actually possible. I mean, we're also discussing about how we can train this model on different regions of the Kiel line, like hotter stars or colder stars.
There's no problem going from the resolution of 28,000 to what is the prism spectra,
the problem is
less than 100?
These are the best spectra which are published, I mean, the least noisy ones.
Well, for prism spectra, they're all published, right?
Right, yeah, but I mean, frequently similar to noise is 2, okay? So that's what you have.
Well, but you have many millions. So
you have many
you also
millions.
have, you also have a million where signal to noise is
Yes,
high.
yeah.
Well, I actually have many millions for the signal to noise.
Yes, you
It's high.
I mean, it would be a challenge to obtain individual alpha elements from a spectrum.
Oh,
which
I'm pretty sure.
Yeah, it won't be big. But as far as
but
temperature, surface gravity, or maybe just the metallicity, I think it is possible.
It is
It's possible for the cannon. Because I have tried this method with the S5 archival data earlier. Like I was trying to see, although I did not proceed with that work, but because typical signal to noise ratios for S5 data was in the range of 1 to 10, so it's like 2, 3 signal to noise. And you would eventually only aim to get temperature, surface gravity, and maybe metallicity, but not like titanium or nickel or silicon, even individual. It's not possible.
yeah, for those with signal to noise 5, of course not.
It's not possible. Yeah. But yeah, for
For
basic
the
stuff,
spectra,
it's
you have many with signal to noise 100.
Yep. Then it is really great. If you have a good training sample, and then we know that there are eventually a good number of lines for a spectrum.
Well, would GALAH be a good training sample for this?
Yes, it will be good. I mean, I really admire this particular part of the canon, that you can actually apply this to any two surveys. Technically, you can apply to any two surveys wherever you want to map the information from. Like if you have a low resolution survey and you have a high resolution data, you want to map it and then predict for the larger data set, you can do it with any resolution. And that includes PRISM and also the GALAH. You can map it and then see how you do it. And some of the earlier works which has been done with this is the Lamos data with Apogee. They have used how the abundances, especially the temperature and metallicities, were predicted for the giants.
That really solved the canon.
Yeah. And in fact, the data release 2 for GALAH used Canon actually to predict the abundances for the total catalog. So there have been different approaches. And yeah, there are a couple of more projects which I am actually working currently to kind of scale this one to different surveys as well. So hopefully soon I'll be able to give results on that as well.
We're looking at cool young stars.
Yeah.
Because they're not in the original trend.
Yeah. Yeah, I mean, that's one thing also we kind of found out, like it's actually very difficult to develop a single universal Cannon model for all the stars in the Kiel diagram. Like it's very difficult because the cool young stars or maybe the hot stars, it's very difficult to kind of bring them into the space, which is why I can actually show you this one. And I was discussing with Yanis earlier. So you see here, we are actually automatically getting rid of all the cool. Because and we are not actually removing those stars forcingly. These are automatically getting removed using the 12-fold validation test, because the spectra here is very kind of difficult when you develop a Canon in a general sense over the total stars, which means the abundances that are getting predicted for these cool dwarfs are outside of the 2 sigma label space of the training sample, which is why we don't do it. But this can be done separately, like you do a separate model specifically for those, which is what I'm discussing with Yanis, and then something like that we can do.
Is there any fear that, like these stars, some other subpopulations?
Sorry.
So, like you said, that these stars get young, cool stars get automatically removed, right?
Yeah.
Is there any fear that you're losing some subpopulations on the other parts of the HR diagram, and you're just not seeing
So,
Yeah, I also wanted to ask, why is there no horizontal branch stars? Because we have them here.
So here I would actually, I don't know if I have actually the original Kiel diagram without the flat stars, but there were a bunch of stars here. There was a bunch of stars here, and there were a bunch of stars here. And they were like all blobbed out because the Canon was not picking the abundances properly, because they are outside again of the 2 sigma label space. But yes, there is always a chance that you actually miss out some prominent information. But when you're developing a universal Canon model for all the stars, it's very difficult to have everything included into a single model. What you can do is you can develop a separate model for each stellar population separately, because then the Canon will only focus on the features for that particular stellar group and won't bother about the other stars. Like for example, you go towards the more cooler end, the cooler giants, the molecules start to be overpowering over the atomic lines, which means you won't be able to get the abundances clearly. For example, like there is one particular neodymium line actually in the RVS range, which is very close to the CN molecular band. You can't predict it. It messes up.
Gaia sausage, you actually need more of those giants.
Yes. Yes. So yeah, then you have to train the model separately for all the stars. In fact, that's actually one of the motives on my second paper, which is why I did not want to develop the model on all the stars, but mostly with giants, because my ultimate aim was to see for GAC, which is part of the giant phase. So that's why we had a subsample of the stars and then trained the canon on top of it. But yeah, the whole process, the whole validation and everything depends on how you're choosing a training sample. I mean, for my target, it took me about a month or so to kind of find out which training sample is engulfing, like it's encompassing all the stars in the sample. Yeah, that's it.